Hey everyone, and welcome to the Explainer. So if you write firmware, you already know that compiling your code and flashing a board is, well, just the very beginning of the story. Today, we're going to pull back the silicon curtain to explore how memory physically works inside a microcontroller. Seriously, think about this for a second. When you hit compile and transfer your C code onto that tiny little square of silicon, where exactly does your program go? I mean, every single if statement, every for loop, every instruction you type, it's literally etched into a physical, microscopic location on the hardware.
And what about the data that's constantly changing? When your sensor reads a temperature and stores it, where is that exact number physically sitting at that exact millisecond?
And when your functions start calling other functions, how does the chip actually physically track the return path? Well, today, we're going to treat the microcontroller like a physical building, and we're going to explore it room by room. Here's our floor plan for today. First, inside the microcontroller. Second, the memory vaults. Third, stack versus heap. And fourth, the complete memory map. All right, let's kick things off with section 1, inside the microcontroller, drilling down. As we descend through the layers of the microcontroller, we actually follow a very specific spatial sequence. We start all the way at the top with flash memory, then we move down into the RAM. Digging even deeper, we hit the registers. And finally, at absolute rock bottom, we reach the peripherals. Those are the actual hardware connections to the outside world, like your timers and communication ports. Now, as we move down this chain, access times get wildly faster, but the purpose of each layer shifts dramatically. Moving right along to section 2, the memory vaults, permanent and volatile storage. First up is flash memory. Think of this as your permanent library. This is where your compiled .text sections and program instructions are physically etched in, locked and loaded the exact moment the system boots up. Now contrast that quiet library with RAM, your hyperactive, highly volatile workspace. This is the physical home for your active variables, which includes your uninitialized .bss and initialized .data segments. This area is just constantly being rewritten as calculations execute on the fly. But what if you have data that changes? But you absolutely need it to survive a power cycle. Enter EEPROM. EEPROM is a totally distinct, specialized vault just for saving critical, permanent data. Now, you definitely wouldn't want to constantly read and write to it every millisecond like RAM, but it is absolutely perfect for saving things like user settings or calibration data that simply cannot be lost when you pull the plug. And finally, we have the registers. These are literally the direct control knobs and levers for the hardware itself. They are incredibly small, immediate access memory locations that are tightly coupled directly to the processor. When you want to, say, flip a pin high to turn on an LED, you are ultimately just writing a 1 or a 0 into a highly specific register. Section 3, stack versus heap, the mechanics of the workshop. So inside RAM, we basically utilize two main mechanics for handling memory on the fly: the stack and the heap. The stack is highly organized, fast, and totally deterministic. It handles function calls and local variables. The heap, on the other hand, is dynamic. It lets you allocate random chunks of memory on the fly while the program is actually running. Let's actually look at the stack's deterministic beauty in action. When a function call happens, boom, the microcontroller pushes its current place in the code, along with local variables, right onto the stack. Nested function calls, they just push more data right on top, building upwards sequentially. And upon return, it simply pops those variables back off, shrinking down perfectly. It's incredibly tidy. Which brings us to a massive question for embedded developers. If the heap allows us to just grab memory dynamically whenever we want, using commands like malloc, why is it practically a forbidden word in embedded environments? Honestly, it boils down to two things: memory fragmentation and determinism. When you dynamically allocate and free memory using malloc, it leaves these little gaps or holes of free memory scattered all over the place. Over time, you might technically have enough total free memory, but it's chopped up into tiny, unusable fragments. In a constrained embedded system with strict deterministic requirements, this garbage and fragmentation will eventually cause your memory allocation to fail, which crashes your entire system exactly when you need it most. And that is exactly why in embedded programming, we usually stick strictly to the predictable, sequential stack and static global variables. And that brings us to section 4, the complete memory map, the blueprint. When we take a step back and look at the unified blueprint, it all just makes sense. You see permanent flash holding the compiled program code in any constants, the things that never change. Over on the active RAM side, global variables sit at the bottom. The heap grows upward, the stack goes downward, and acting as a safety buffer right between them is your free memory.
Let's ground all of these abstract concepts into real-world embedded scenarios for a second. Think about your actual projects. Your core firmware, locked safely in flash. Those calibration constants you need to save between power cycles. They live in the EEPROM. When you check an LED state or store an array of ADC sensor readings, those exist right there in your active RAM. When your program jumps from main to a sensor reading function, that jump happens securely on the stack. And when data is streaming in from your serial port, that UART receive buffer is mapped as a contiguous region right there in RAM.
Understanding this blueprint is literally everything when it comes to optimization. Because the heap grows up and the stack grows down, they share the exact same physical real estate. So what happens when you run out of free memory and they physically collide? Well, that is the dreaded stack overflow, a catastrophic failure where active variables overwrite function return addresses and your entire system goes down in flames. It highlights perfectly why mastering this physical memory map is the highest stakes art in embedded engineering. Well, that's it for today. Thanks so much for joining this explainer. See you next time.